Hello, my name is Daniel Zlogalactos, and today we're going to be doing a dynamical analysis of a Jeep suspension system. As you can see, this image below is a design based on a Jeep Wrangler TJ from 1997 to 2006. In each of the four corners, you can see a spring and a damper. Some information or assumptions we're going to have is that the weight is going to be based off of a 2008 JK Rubicon, which has a total weight of about 4,600 pounds. It's a little bit above the average. That's what we're going to go with. The weight distribution of this vehicle is 1,200 pounds on each of the quarters in the front and 1,100 pounds on each of the quarters in the rear. That's 544 kilograms and 499 kilograms, respectively. We're going to assume the spring constants to be 22 kilonewtons per meter all across the board. And this is just a basic visual representation of a simplified suspension for the front axle or the rear. The spring is on the left and the damper is on the right. Using Hooke's law, we can solve to see the displacement in the vehicle for its static equilibrium position. So it's going to drop 0.243 meters in the front and 0.223 meters in the rear. The natural frequency is equal to k divided by m, square root k divided by m. And we find that the natural frequency when converted to hertz is 1.01 hertz in the front and 1.06 hertz in the back. Damping ratio it basically means that when the damping ratio is below 1, it's the system is underdamped, which means it will oscillate. Like if the car runs over a pothole or something, the suspension is going to continue to oscillate, but eventually go back to its equilibrium position and die out, but it'll take a while. If the system's overdamped, it's going to hit the pothole and it's going to be initially displaced by it, and eventually it's going to go back to its static equilibrium position, but it's going to take quite a while. When the system is critically damped, it does the same thing of when it's overdamped, but it does it as fast as it possibly can. So it will get displaced, and then it'll very quickly go back to its static equilibrium position. So critically damped is the best way to get rid of all vibration, and does it the most efficiently. So if we make this equation equal to 1, we can solve for the damping constants to be 6,919 newtons per meters per second in the front and 6,627 newtons per meters per second in the rear. Under that, once we get that, we can solve for the damp natural frequency, which is just 0, which makes sense because the system is critically damped and it's not oscillating. So some changes that we can make to make this more realistic, because nobody drives a car that's that stiff, that doesn't oscillate. That would just be very uncomfortable. So a passenger car a passenger car is generally a comfortable ride at half a hertz to 1 hertz. And Wranglers generally have a stiffer suspension since they're more geared towards off-roading. So we're gonna say we're looking for about half a hertz. The rear spring constants are going to be changed to 27 kilonewtons per meter, and that's just because some people like to have stiffer springs in the rear and softer in the front. So when the car runs over potholes or something, the front wheels will have as much contact with the ground as possible, and it'll kind of hug the ground. And then the rear, if it's stiffer, it's going to give you more control when turning and maneuvering. So we're also going to add a passenger and a driver, about 181 pounds each. That's the national average. So the new frequencies are calculated to be 0.98 hertz and 1.12. We want the damp natural frequency to be half a hertz, so we solve the damping ratio for that and the damping constant thereafter. You get 6,121 newtons per meters per second in the front, 6,889 in the back. And if we analyze the system, on the left side, we get an equation of motion. F is equal to mx double dot plus cx dot plus kx. When we use the Lagrangian equation, which includes R, the energy dissipation due to viscous friction because of the dampers, we get the same exact thing. When these are T, V, R, and Q, where V is potential and T is kinetic, the Lagrangian is T minus V, and the Hamiltonian is T plus V. Thank you very much.